Hello my dear students, how are you? Hope everyone is well. Today I am going to discuss about some common realization questions about the Wheatstone Bridge. The first question is, why did we use low voltage battery? Okay, we always use low voltage battery, not high voltage battery. The cause is, if we use high voltage battery, then the high voltage battery will supply high current. Due to increase of current, when this current passes through the resistances PQRS, due to Joule's effect, here heat will be produced. Okay, and you know the produced heat is H equals to I square RT. Okay, and you also know if heat increases, then the value of resistance also increases. As a result, due to change of the value of resistances PQRS, the balance condition will be incorrect. Okay, and we will not able to determine the null point. As a result, we cannot determine the unknown resistance of a conductor. Due to this problem, we don't use high voltage battery in the circuit. Hope you got it. Well, the second question is, you know the potential at point A, VA, is greater than the potential at point B, VB, and the VB is greater than the potential at point VD at point B, and the potential at point D is greater than at point C. Okay, that is VA greater than VB greater than VD greater than VC. The question is how this is happened. Okay, now here the battery. Okay, we consider that the EMF value of this battery is 5 volt. Okay, this terminal is positive and this terminal is negative. You know the potential at the positive terminal is 5 volts. Okay, and the potential at the negative terminal is 0 volt. Okay, now the point A is directly connected with the positive terminal and there is no resistance here. Therefore, the potential at point A will be 5 volt. Okay, so we get here VA equals to 5 volt. Okay, now along AB there is a resistance. Suppose the value of this resistance is 10 ohms. Okay, due to this resistance there will be a voltage drop. Suppose due to 10 ohms the voltage drop is 3 volt. As a result, we get here the potential is 2 volt. Okay, VB equals to 2 volt. Okay, now at point C, this point C is directly connected with the negative terminal of this battery, as the potential at the negative terminal is 0 and there is no resistance here. Therefore, the potential at point C will be 0. Okay, now at point D, if we use a resistance which is greater than the value of P, suppose it is 20 ohms, then the voltage drop will be greater than the path AB here. Okay, suppose here the voltage drop is 4 volt. Therefore, the potential at point D will be VD equals to 1 volt. Okay, so we are getting that VD equals to 1 volt and VC equals to 0. So from this result it is clear that VA is greater than VB and VB is greater than VD and VD greater than VC. Hope you got it. Next, the question is why we cannot determine low or high resistance of a conductor by using Wheatstone's bridge. The cause is, if we want to determine low resistance, then suppose we have to connect the conductor across DC, okay, then the value of S is less than 1, okay, the value of S or conductor will be less than 1. In this case, the resistance of the wires AB, BC, CD and DA will be also less than 1, because we consider these wires has no resistance, but actually there is no wires which has zero resistance, which has no resistance. You know, the wire which has no resistance is called superconductor, but here we are not using the superconductor. These wires has also their intrinsic resistance, which is less than 1 ohms. That's why the resistances of the wires is nearer to the resistance of the conductor or the S. Therefore, we cannot determine accurately the null point in this case. That's why it is not possible to determine the resistance of conductor or whose resistance is less than 1, okay, or low resistance. Again, we also cannot determine the high resistance of a conductor. The cause is that if the resistance of conductor is high, then the value of S will be also high. Suppose it is 2000 ohms, then what will be happen? Then current will not able to flow through this resistance along the DC. As a result, the sensitivity will be decreased. The sensitivity of this bridge will be decreased. Due to this, we will not able to determine the null point. Okay, so it will be not possible for us to calculate the resistance of the conductor. Therefore, arising the two problems, we cannot determine the low resistance and high resistance of a conductor. Hope you got your answer. Now I am going to solve some mathematical problem by using the Wheatstone Bridge. Okay, first I will show you how we can determine the equivalent resistance by using the Wheatstone Bridge. Okay, stay with me. Now the problem 1. Here the problem 1. Okay, we consider a circuit like as this. Okay, the value of this resistance is, suppose P equals to 10 ohms. Its resistance is also 10 ohms. Here the resistance is also 10 ohms. The resistance of S is 10 ohms and the resistance of this is 10 ohms. Now the question is calculate the equivalent resistance. Okay, the equivalent resistance R equivalent is what? We have to calculate it. We can calculate the equivalent resistance of this circuit by using the Wheatstone Bridge, because its configuration looks like Wheatstone. Okay, and there are 1 2 3 4 5 resistance. If you get any circuit which consists 5 or 6 resistances, then you have to consider that this problem is related with the Wheatstone Bridge. Okay, you can use Wheatstone Bridge balance condition to solve the problem of that circuit. Okay, now here we are getting that the ratio of P by Q is 1. Okay, P by Q is 1, and here the ratio of R by S is also 1. That's why the circuit follows the Wheatstone Bridge principle. As a result, the potential at this point and this point will be same. Suppose the current is flowing through this terminal to this terminal. Okay, as the potential at point this point and this point is same, then there will be no current flow through this resistance. So we can't neglect or we can't remove this resistance. Okay, then it is clear from this circuit that P and Q, these two resistances, are connected in series. Again, the resistances R and S are connected in series, and they are both connected parallel to each other. So we can rearrange this circuit as P and Q as they are connected series, so their equivalent resistance is, suppose RS1 equals to 20 ohms. Again, R and S also connected in series, therefore their equivalent resistance RS2 is also 20 ohms. Okay, now these two resistances are connected in parallel, therefore their equivalent resistance will be 1 by Rp, okay, equals to 1 by 20, 1 by Rs1 plus 1 by Rs2, or here we can write Rp equals to Rs1 into Rs2 divided by Rs1 plus Rs2. Now putting the value, we get here 20 into 20 divided by 20 plus 20. So we get 400 divided by 40. So finally we get the equivalent resistance is 10 ohms. Okay, the equivalent resistance is 10 ohms. So hope you got it. And now the problem 2. It is a little bit different from the problem 1. In problem 1, here along this line there was a resistance, but here there is no resistance. It means these two points are connected by only a wire without resistance. That is, here the line is shorted. Okay, then what will be the equivalent resistance of this circuit? Okay, now as these 2 points are shorted, that is here the both potential will be same. Okay, here the potential and this potential will be same. That's why we are getting that the current when reach at point A, it will be separated into 2 paths, and here they will be meet together. Okay, that's why P and R will be in parallel. Okay, next here from this point it will be divided again into 2 paths along across Q and S, and they will be meet at point B together. Okay, that's why Q and S are parallel to each other, but this side and this side are connected in series. So we can rearrange this circuit like as this is point A, this is the resistance P, which is 10 ohms, this is the resistance R, which is also 10 ohms, and it is parallelly connected, it is connected series with Q and S, but Q is parallel with S. Okay, here the value of Q is 10 ohms and here the value of S is 10 ohms. Okay, we can rearrange this circuit like as the circuit which I drawn below. Okay, so what is the equivalent resistance of P and Q? Suppose as they are parallel, the equivalent resistance will be 1 by Rp. 1 equals to 1 by P plus 1 by Q, or Rp1 equals to PQ divided by P plus Q. The value of P is 10, Q is also 10, and here 10 plus 10. So we are getting that 100 divided by 20. So we get 5 ohms here. Okay, similarly, the equivalent resistance will be 1 by Rp2 equals to 5 ohm. R by 2 is 1 by Q plus 1 by S, or Rp2 equals to 5 ohms. Because their value are same, that's why we can directly write that the equivalent of these two resistances will be also 5 ohms. But these two circuits are connected in series, that's why their equivalent resistance will be Rs equals to Rp1 plus Rp2, that is 5 plus 5 equals to 10 ohms. This is the equivalent resistance of this circuit. Hope you got it. Now the problem 3. The circuit is given here. You have to calculate the equivalent resistance of this circuit. Okay, if we analyze this circuit, then we get these resistances are not connected in series nor parallel. So how can we calculate the equivalent of this circuit, equivalent resistance of this circuit? Okay, to get the equivalent resistance, we can rearrange this circuit like as, suppose this point is B, this point is C, this point is D, this point is E, and we take this point is F instead of B. Okay, so it is A, B, C, D, E. Now we can take this resistance here. Okay, there is a resistance between A and B. Okay, A, B. We are taking this resistance here, so we can remove this leg. Now there is a resistance between B and C. There is a resistance R between B and C. Okay, we can take this resistance here, this resistance here, B to C. So we can remove this resistance. Okay, now there is a resistance between B and D. Okay, we can take this resistance here. Okay, between B and D. This is the resistance. Now there is a resistance between the point C and E. it is also R. Here the point is C and E. Okay, C and E, we can take this resistance here. This is C and this is E, and here the resistance is R. Okay, now we can remove this leg. Okay, now there is a resistance between C and D. Okay, so we can take this resistance here. This is C and this is D. Okay, so we remove this resistance. Okay, now there is the last resistance between D and E. Here the D and here the E. So we can take this resistance here and we can remove it. Okay, finally we get the rearranged configuration here. Okay, here we are getting that the ratio of R this side and this side is 1, and the ratio of this side R by R is also 1. So the circuit obeys Wheatstone Bridge principle. Okay, so the potential at point C and D will be equal. As a result, no current will flow through this resistance. Okay, so we can remove it. Okay, so it is clear that this resistance R and R, now they are connected in series, and the resistances R and R, these two resistances are connected in series. Okay, so again we can rearrange this circuit like as between A and B there is a resistance R. Okay, this is the resistance. Now this R and this R together is 2R. Okay, it is 2R. Again here the equivalent resistance is also R plus R is 2R. Okay, and this point is E. Now these two resistances are connected in parallel, and it is also connected in series with this resistance. So we can again rearrange it as R. This is A to B, and here the resistance or equivalent resistance of two resistances is suppose RP. Okay, this point is E. Now what is the equivalent resistances of the resistance of these two resistances? It is 1 by Rp equals to 1 by 2R plus 1 by 2R. Okay, so from it we can write Rp equals to 2R into 2R divided by 2R plus 2R. So from above we get 4R square divided by 4R equals to R. So here Rp is R. Okay, now as R and Rp are connected in series, therefore again their equivalent resistance will be Rs, and it will be Rs will be R plus R equals to 2R. So this 2R is the equivalent resistance of this circuit. Now the problem 4. Here the circuit is given. You have to calculate the equivalent resistance. This circuit looks like a ladder. That's why this circuit also called ladder circuit. Okay, if we analyze this circuit, we see that these resistances are not connected in series nor in parallel. How we can calculate the equivalent resistance of the circuit. Okay, here if we take these two resistances ratio, their ratio is 1:2, and here the ratio of these two resistances is also 1:2. So these sides follows the Wheatstone Bridge principle. They are in balance, therefore no current will flow through the resistance 7 ohms. So we can't remove it. Okay, again, if we take the resistance ratio of two resistances, we get 1:1.5. Similarly, here the ratio of two resistances is 1:1.5. That's why it is imbalanced. So no current will flow through the resistance 12 ohm. So finally, what we see here, we see that 5 ohms, 10 ohms and 15 ohms are connected in series, and 10 ohms, 20 ohms and 30 ohms also connected in series, but they are connected in parallel in each other. So we can consider this circuit in another way, that is the ratio of the resistances which are given upper side is 1:2:3, and the ratio of these resistances is also 1:2:3. As their ratio are same, therefore no current will flow through the 7 ohms and the 12 ohms. So we get the equivalent resistance of the three resistances are here 30 ohms, and here the equivalent resistance of these resistances is here 30 plus 30, 60 ohms. Okay, now 30 ohms and 60 ohms are parallel each other, so their equivalent resistance is 1 by Rp equals to 1 by 30 plus 1 by 60, or we can write here Rp equals to 30 into 60 divided by 30 plus 60. Okay, next we can write Rp equals to 1800 divided by, here we get 90. Okay, so the equivalent resistance of this circuit is 20 ohms. Okay,